Today we are going to be talking about graph coloring techniques. This is called a mini excursion, a mini lesson, if you will. We're going to be spending 2 days on this topic. So one thing you should already have are 4 colors. So it doesn't matter what 4 colors you are using, but you need 4 colors, and you could also use like white by leaving something uncolored, or you could use your pencil as a color. But you need 4 colors for this. Today we're going to start this graph coloring techniques and just a little bit of history behind where this is. In the mid-1800s, we had a guy, Francis Guthrie, and he was trying to make a map of the counties of England. And the idea is that he wants to use as few colors as possible. So after a little trial and error, he thought he could do the map in 4 colors. Now over here at the right, and yours doesn't show out very well on your black and white copies, but you can see that this is 5 colors right here. And the idea with map coloring is that you don't want the adjacent countries to be the same color, or else you can't tell, or sorry, the adjacent counties in this case. So we want to make sure they're different colors so you can see where the borders are. But we don't want to use every color a different color because that's not very visually appealing. And in the time of Francis Guthrie, they also wanted to use fewer colors because colors were expensive. You had to use different ink for different colors. It wasn't like our modern day laser jet printers where we just pick whatever we want and it prints whatever we want. So the fewest number of colors made it a cheaper graph, and money was important to them. And also having the different counties being a different color made it visually appealing as well. Now, he decided again that he thought that he could color the map in 4 colors, and he conjectured that you could do any map in 4 colors, no matter what it was. And so people started trying it out. And what they wanted to do was, mathematicians really got a hold of this, and they wanted to be able to prove that any planar map, that means a 2-dimensional map with geometric shaped sides, could be colored using only 4 colors. So over 100 years, and we get to about 1976, and we have something called the 4-color theorem. So Kenneth Apple and Wolfgang, I'm probably going to say this wrong, Haken, they actually proved this. Now, many people refuse to accept this theorem as a fact, though, because they used a computer to help him. So the reason why we're interested in this today is for a couple of reasons. The first thing is that this was the first time where a mathematical theorem was proven using a computer-aided proof. Or in other words, because the mathematics was too difficult to do by hand, they had to use a computer to help them go through the iterations and go through the proof of this. And a lot of people still debate this and say, hey, you know, if you can't do it by hand, it doesn't count. But this was a computer helping them out. So that's why it took until 1976 to prove this, was because they needed that technology to help them out. So that's why we're interested, because this is this is the first time that a computer was significant in the proving of a mathematical concept. We also use it today for a kind of map labeling or graph labeling technique, which we're going to talk about. Okay, so for today, let's talk about the map coloring rules. So when we are coloring a planar map, that means not vertices with edges, but something that looks like this, a 2-dimensional shape, regions who share a common edge cannot be the same color. So what that means is that if I have this corner right here, and I'm going to color this yellow, okay, I cannot make this area down here yellow or the one right next to it yellow, because they share an edge. Now, if the graph just touches at a corner, so if you think like vertical angles, so if you have 2 lines crossing and you are just adjacent at a diagonal corner, so 1 point of adjacency, touch. Okay, you can be the same color. So like these 2 could be the same color, but I can't have this bottom left-hand corner be yellow because it shares an edge. Now the one in the upper right-hand corner could be this aqua color I've got. Okay. So those 2 can be because they just touch at that corner. Now I have a little bit of an issue here. This rectangle right here definitely shares a side with this blue, and it definitely shares a side with the yellow. So it has to be a different color entirely. Okay. Inside here I've got this sharing pink, so that can't be pink. I've also got it sharing with yellow. It can't be yellow. I could make it aqua though. So I was able to color this little planar map with 3 colors. 4 if we count my little overlap right there. So here's one, and let's try and color this, and we're going to use a maximum of 4 colors. That means no more than 4. So no adjacent regions, so regions that share a common edge that can't be the same color. And what a lot of people try to do is sometimes kind of approach this by either starting from the center and sort of working your way out, or starting at a corner and working over. I like to start from the center. So I'm going to start here with this circular region. And then I have a very large area around it, which I know can't be yellow. So I'm going to go ahead and color that, this blue color. Okay. Coloring, and you all are coloring as well. Okay. Now when I look at the corner, I see that this corner shares this edge with the yellow. It also shares the edge with the blue, which looks like it is time for us to have a different color entirely. Okay, so I'm going to go ahead and pull out a third color for this area. And as you're doing these notes, remember that if you are kind of get behind, you can just sort of do some little light scribbles to remind you what color needs to go in what place. Okay, over here in the corner, I see I'm sharing an edge with pink and with blue, so I'm going to go back and I'm going to use my yellow right here. Okay. And down here, I'm sharing an edge with yellow and with blue, so I'm going to go back and I'm going to color my triangle here pink. Okay. Triangle in the corner right here could be pink because it just touches that, or it could be yellow. Let's make it yellow to keep things interesting. Okay. Could also have yellow right here on the sharing that diagonal, and yellow right there because all they do is touch on the corner. And I could use pink or blue right there. Oop, can't put pink there though. Okay, that shares a little pink edge up here, so I'm going to switch back and use my blue. Now you notice that I said using a maximum of 4 colors, and I was able to do it with 3. You may not be able to do this with 3. You may need 4. So if you find yourself ever where you're like, oh no, all 4 colors are touching, or all 3 colors are touching an area, then you may have to pull out that other color. And that's fine. Okay, so those are map colorings. Now, the other aspect of this is vertex coloring. Vertex coloring is a kind of graph labeling where no 2 connected or adjacent vertices can be the same color. So here is a graph, and so what that means is I'm going to start off and I'm going to say, I'm going to make this one up here yellow. Now, if I make that yellow, the ones that are connected it cannot be yellow. So maybe I decide to make this one blue. If that's blue, I could also make this one blue here because it's not connected to my other blue one, and I could make that blue as well. Okay, this one right here is connected to a blue, so maybe I'll make that one yellow. Now this guy right here can't be yellow, it also can't be blue, so I'm going to need to pull out a different color. How about pink? Here I've got one that can't be blue because it's touching blue, and can't be pink, but I could make it yellow. So even though they're close to each other, they're not adjacent to each other. Here can't be yellow and can't be blue, so how about pink? On this corner, can't be yellow, can't be blue, could be pink. Now I've got 2 pinks and a blue, so I'm going to go with yellow. Again, I was able to do this with 3 colors. That's great. All right, here I'm going to start up here at the corner. I'm going to make this yellow. I know that neither one of these can be yellow, so how about blue? This one is connected to blue and to yellow, so maybe I make this one pink. Here, this corner is touching blue and it's touching pink, so maybe I make that yellow. And now as I get to the corner here, I have pink and yellow and blue. They're all touching that, so I need to go with my 4th color. Now the thing about vertex coloring, when you're dealing with a vertex, you may need more than 4 colors. And that's okay. So a planar graph uses our 4-color theorem. With a planar graph, we should be able to color that using only 4 colors. But with a vertex graph, we need as many as we need on this case. Okay, there's no way to determine that. So vertices have different rules than planar graphs do. Another thing that we're interested in is something called chromatic coloring. Now you may hear that word monochromatic, usually means it's in shades of gray, or sometimes we use the word chromatic to talk about, different shades of one color. In our case, chromatic coloring is when we are working on coloring the vertices in different colors, and we're interested in how many colors does it actually take. So a K coloring of a graph is a coloring of the vertices using K colors. So for example, find a 3 coloring. That means that we would use 3 different colors to color that. Okay, so here's a case where I'm using 3 different colors. I've got red, I've got blue, I've got green. This is a 3 coloring. It used 3 colors. We have to satisfy the requirement that adjacent vertices are colored with different colors, so I can't break the rule of vertex coloring. The chromatic number of a graph is the smallest number of colors, K, for which it can be K colored. So am I able to use a 3 coloring? Sure. What about a 2 coloring? Well, if I make this one red and this one blue, then I could make this one red. Now this would be a 2 coloring. It took 2 colors to do this. A 1 coloring, that means I'm only allowed to use 1 color. So if I make this red, I go on to this next one. I'm only allowed to use 1 color, but I can't make it red because it's attached. That would make this a 1 coloring impossible. Okay. There's no way to use 1 color to do this and not break the rules of graph coloring. So what that means is that the fewest number of colors we could legally color this is 2. That's called the chromatic number. Okay, this graph could be colored using 2 colors. All right, so what about find a 4 coloring? Now there's 4 vertices, so a 4 coloring just means that it's going to take us 4 colors to do this with. Okay. No problem. All right, 3 coloring means I need to use 3 colors. If I make that one blue, I can't make either of these blue, so I'll make this one red. This one can't be blue or red, so how about green? And then this last one right here could either be blue or red, but not green, so I'm just going to pick red. So there's my 3 coloring, legally colored using 3 colors. And what about a 2 coloring? Okay, if I go to do a 2 coloring, I've got blue, and I could make this red. But then I've got a problem. I'm only allowed to use 2 colors, so I'm using blue and red. I can't make this one blue or red. That's a problem. This is impossible. Sometimes you have to use a little bit of reasoning to do this, but it looks to me like the chromatic number of this graph is a 3. So the smallest numbers for which we can legally color this graph is 3. Okay, now we already talked about complete graphs in our last chapter. You were very excited about that. Remember that a complete graph means every vertex is connected to every other vertex. So here's a complete graph, K sub 4. Here's a complete graph, K sub 5. Okay, so every vertex is connected. And the interesting thing about a complete graph is because each vertex is connected to every other vertex, it basically means that each vertex has to be a different color. So the chromatic number is the same as the number of vertices. So here's what I'm talking about. Here's K sub 4. If I make this vertex red, I can't make any of the others red because they're all connected. And if I make this one blue, I can't make any of the others blue because they're all connected. And again, green, nobody else can be green. And then no one else could be black. They need 4 different colors to make this work because they're all connected. Here's another one, K sub 5. Okay, so if I color in my vertex, if I make this one black, I can't make any of the other ones black. And if I make this one red, none of the other ones can be red because they're all connected. I can make this one blue, but none of the others can be blue. Let's see, we could make this one green, but none of the others could be green. And I could make this one pink, but none of the others could be pink. So the chromatic number for a complete graph with 5 vertices is going to be 5. So if you know you have a complete graph, you don't really need to color it to know the chromatic number. If everything is connected to everything else, the chromatic number is going to be the same as the number of vertices. So K sub 24, I don't need a picture of. I know it's going to take me 24 colors to do that. You can also look at circuits. A circuit consisting of n vertices is called C sub n. So here is a circuit. Notice that means it could be traced without lifting its pencil. It starts and ends at the same place. Here's C4. It says, what's its chromatic number? So if I try to do this in the fewest number possible, I know it's going to take me at least 2 colors because those can't be adjacent. Do I need 3? No. So it's going to take us, I can't do it with 1, but I could do it with 2. Okay, so chromatic number of C sub 4 is 2. C5, if I make this one red, this one can't be, but this one could be. This one can't, and this one can't. Okay, I could make this one blue and this one blue, but then this guy down here is going to have to be a 3rd color. So C sub 5 is going to be 3. What you usually end up with is if that you have an even number of vertices in your circuit, your chromatic number is going to be 2 because you should be able to just alternate every other one. And if your number is odd, then your chromatic number is going to be 3 because you can alternate every other one until they meet up and you're going to need that 3rd color. Okay. One way to approach graph coloring is with something called the greedy coloring algorithm. This is a way that you could program a computer to do your graph coloring for you. So any of you guys who are interested in computer programming, if you were to look for the greedy algorithm, this is something that a lot of programmers use. The first thing you're going to do is going to make your list of colors. And you would want to put your favorite color on the top. And list out your colors, and this is going to give you sort of a priority. These are the colors in the order I wish to use them. The next thing you're going to do is make a list of your vertices. Now, I'm actually not going to list them, I'm just going to look at them. Most of the time, you want the biggest degreed vertex first, or the vertex of highest degree. You want to color that one first. So you're going to color your first vertex with your first color. So I look, I have 2 degree 4s, so I want to start with there. And I would make that first one my first color, red. And then I would go to the next degree 4 and I'd say, can I make this red? No. So I move down to the next color on my list, blue. Then I would look at my next highest vertex. It's degree 3, it's over here, and I would say, can I make this red? Nope. So I go down my list. Can I make it blue? Nope. So I would go down my list again. Looks like I'm going to need to make that green. And again, can I make this red? Nope. Can I make it blue? Nope. Can I make it green? No. So it looks like I'm going to need to make it gray. Now, according to the greedy coloring algorithm, that leaves me with this one vertex up here on the top, and I would say, which color should I make it? So it can't be red, it can't be blue, it can be green though. So according to the greedy coloring algorithm, I would make that green. And you would just assign these to a computer, and the computer would work its way through your list, following your rules to make that work. Here's another kind of crazy graph. I'm going to look for a high degree vertex to start. This one looks like degree 4. That looks like a pretty good place to start. I'm going to make that red. Here's another degree 4, 1, 2, 3, 4. This one can't be red, though, because it's connected. So I'm going to go down to the next number in my list, blue. Okay. Here's another degree 4. I would ask myself, can this be red? Looks like it. And then here's another one. Can this be red? Nope. That could be blue. And the idea is you use the same color over and over and over again as long as you can. You only use these other colors if you absolutely have to. All right, I've got all my degree 4, so I'm going to start hopping around degree 3 now. Here is a vertex of degree 3. Could it be red? Yes. Here's a vertex of degree 3. Can't be red, but it could be blue. Here's a vertex of degree 3. Can't be blue, can't be red, so I need to move on to my next color, which is green. This one can't be red, and it can't be blue, so I could make it green. Can it be red? Yes. Can it be red? Nope. Can it be blue? Nope. Can it be green? Now, by reserving those colors, you tend to help yourself not paint yourself into a corner. Gives you more options. So instead of arbitrarily just grabbing colors and seeing what works, this gives you a strategy to use. Now, this doesn't always give you the best answer, but it does give you a strategy to at least approach coloring these if you get a little stressed out by the randomness. Sudoku is a game that a lot of people play, and it's actually an application of graph coloring too. The way Sudoku works is that you have a box with all the numbers from 1 to 9, and you're trying to get all of each row, each column, and each box, 3 by 3 box, to have the digits 1 through 9 exactly once. Okay, so as I'm looking through there, for example, I see I've got a bunch of 3s. So let's say I look at this 3 and this 3 and this 3 and this 3 and this 3. And the way we would look at this and say, okay, I need a 3 in each box, in each row, and in each column. So I've already got a 3 in this column, and a 3 in this row, and a 3 in this box. Okay, so I can't really do anything else there. Maybe I look here. Here's a 3, so I've already got a 3 in this column. And I've already got a 3 in this column. So that means down here in this box that doesn't have a 3, I can't put one here because I've already got one in that column. And I can't put one here because I've already got one in that column. So I've only got one more space in that box. That has to be my 3. Okay. So this is kind of our idea of how Sudoku works. We're looking to have this connected. Now, we're not going to actually spend some time and fill this in. Here's what I'm interested in. If you were a computer, and you were looking at this box and trying to see how would the computer see this. Okay. They wouldn't see it as a grid, they would see it as a set of vertices. And I have this vertex in this corner. I'm going to make this yellow. And just like it's a 3, that's like a color. And this 3 has to be the only 3 in this box, which means that 3 is the only one that could be yellow. Okay, or that corner is the only one that could be yellow. So if each of these are a vertex, that means that each of those are adjacent or connected to that yellow vertex. Okay? So none of the rest of them can be that color. And furthermore, it's the only one that can be a 3 in that whole row. So it's not just that box that it's in, it's also the row, and it would be connected to everything in that row. And it also can be the only 3 that can be in that column. So it would look down like so, and it would be connected. Now the thing that kind of blows my mind when I'm looking at this is that that's how a computer would just see this one vertex. And every vertex in the entire graph would be connected at this level. So if you were to program this into a computer and have a computer to solve a Sudoku problem or one to randomly create Sudoku problems, this is how the computer is going to see it, as a series of connections. I wouldn't want to draw this picture, but this is just that one vertex as a connected graph. Okay, so imagine every single one of those. And again, if you like Sudoku, there's more of that, but that's an application of graph coloring. Here's another application of graph coloring. We have scheduling problems that require some tasks to have shared resources. So sometimes we might represent those as a graph and try to use our room. So like interviews or air traffic control, we're talking about runways. We want to make sure that the resources aren't being used at the same time. So the computer programming we would do to solve those is an application of graph coloring where we would consider our resources to be vertices. And if they can't be used at the same time, we would say they can't be the same color. There's a computer programming topic called register allocations for compiler programs. Those of you who are interested in computer science will come across this someday, and that is another application of graph coloring. Bandwidth allocation to radio stations. You're driving along and you're listening to your radio station, and all of a sudden your music fades out and becomes something else. Okay? And the reason why is because that radio station, okay, is only at a certain bandwidth, and as soon as you drive down that bandwidth, it becomes another radio station. Okay, so your radio can only pick up that signal while you're in that station. Okay, as soon as you drive out, you're going to turn into a different station there. So you can think about this as being a different color, or things that can't share the same frequency. If you have two stations that are too close to each other, you can't have the same dialer station on there. Okay. All right, so let's do a little graph here. Let's use a coloring program to solve this. Okay, so you're a wedding planner organizing the rehearsal dinner before a big wedding. There are a total of 16 people attending the rehearsal dinner, and we're going to call them ABC, etc. The bride and groom sit down and they tell you, A doesn't get along with E, F, G, or H. B doesn't get along with C, D, or H, etc. In other words, we're going to call this the graph O hatred. Okay, we have all these people who are coming to the rehearsal dinner and they can't stand each other. So what we would like is for A to not have to sit at the same table as F, G, or H because A doesn't get along with them and it's just going to make everybody difficult. And they say, can you please find a way to sit everyone so that they can get along? How many tables are you going to need? And where do we tell them that they're going to sit? Okay, so as a coloring program, the first thing I'm going to do is I'm going to make a vertex. And remember, we're going to color that vertex, so make it an open vertex. And we're going to create one for every person coming. So it looks like we're going through H. So A, B, C, D, E, F, G, and H. And the idea is that we don't want A to have to sit at a table with F, G, or H. So we're going to picture each of our tables as having a different color tablecloth. If we want to make sure A isn't sitting at the same color table as F, G, or H, then we need to, on the graph, make those adjacent. So A needs to be connected to F, and then we won't color them the same color. A doesn't like G, and A doesn't like H. All right, so I've got that one. B doesn't get along with C, D, or H. So we don't want B to be at the same table as C. We don't want B to sit at the same table as D. And we don't want B to sit at the same table as H. C doesn't get along with B. I've already got that one. C doesn't get along with D. C doesn't get along with E, or G, or H. C seems like a very pleasant person. Ha. All right, B, D, E, G, or H. D doesn't get along with B. I've already got that. C, already have that, or E. E doesn't get along with C, or D, or F, or G. F doesn't get along with A. F doesn't get along with E. Have both of those. F doesn't get along with G. G doesn't get along with A. I have that. Or C. Got it. Or E. Or F. Already have all of those. H doesn't get along with A. We've got it. Or B. Or C. Okay, so here we go. Okay, so I'm going to start off with table 1. And usually what we would like to do here is we would like to assign a color to that table. I'm going to make that my red table. And I'm going to look at this and say, who is my most difficult client here? Who do we want to seat first? Who is going to cause us the most trouble? And I think if you look at this, it's definitely C. Okay, C has the most amount of hatred in their life. They need to be seated first because they are the most difficult. So we're going to put at table 1, we're going to put C. C goes to the red table. All right. And then I would go to my next most difficult client here. Looks like E has degree 4 and G has degree 4. So I could start with one of those. So let's just start with E. Could I sit them at the red table? Nope. All right, so they need a new table. So I'm going to say table number 2. And I'm going to put a blue tablecloth on that table. And I'm going to sit E there. Okay. All right. And then G is also degree 4. I need to give them a separate table as well because they can't be at the red table or the blue table. So how about table number 3? And we will put a green tablecloth on that table. And we will put G at that table. All right, so we're making some good progress here. All right, so how about somebody who is degree 3? Well, here's F. F is degree 3. And I would say, can I put them at that red table? Or the green table, or the blue table? They can't be at the green or the blue, but we sure could put them at the red table. Let's go ahead and do that. Okay. Here's someone else that is degree 3. D is degree 3. B is degree 3. A is degree 3. See, who's the most connected? Looks like A here has already got 2 connected to it. Let's go with that. All right, so A can't be red, and it can't be green. So maybe we make A blue. Okay. All right. How about D? D is connected to red and to blue, so maybe we can make them green. D. All right, we're making progress. H is connected to A, which is blue, and H is connected to C, which is red, so we should be able to make H green. And now, B is connected to green twice and to C, so B should be able to sit at this blue table as well. So I should be able to do this like so. A doesn't get along with F, G, or H, no problem, etc. Everybody should be okay sitting at these tables. Now earlier when I did this, it actually took me 4 tables. So you may be able to do it with more tables. You may have a little bit different here, but your answers could vary. Okay, so if you had people sitting in different places, as long as nobody who hates each other is sitting at the same place, we should still be okay. All right, graph of hatred. Now we got everybody sit down. We're excited. Here's another one. Here the FCC monitors radio stations to make sure that their stations do not interfere with each other. They prevent interference by assigning appropriate frequencies to each station. How many frequencies... they prevent interference by assigning appropriate frequencies to each station. How many frequencies are needed for the 6 stations shown at the distances in the table if 2 stations cannot use the same channel if they are within 150 miles of each other? Okay, so A, B, C, D, E, and F. All right, so I'm just going to go each row here. You can't be the same station, or you can't use the same frequency if you are within 150 miles. So A, let's see, within 25, 77, and 106. A is too close to B, D, or F to be the same color. So A can't be the same as B, A can't be the same as D, and A can't be the same as F. Now, they should be okay if they're the same frequency as C because that's outside that 150 miles, or E because it's outside the 375. All right, so B can't be the same as A, which you've already got, within 150. Looks like D is too close and E is too close. It's right on the edge, but it's still too close. So D is 51. That is B to D. And we also want B to E. Vertex C, within 150 miles of, looks like vertex C is within 150 miles of D only. For vertex D, it's too close to A, and to B, and to C, and to E, but not to F. So we've got A, we've got B, we've got C, we still need E. Vertex E is within 150 miles of B, already have that one. And D, already have that one, so that one's good. Vertex F is within 150 miles of A, which we already have, and the rest of them are outside that range. Okay, so we're going to start with our first frequency. So frequency 1. Maybe we'll call this the red frequency. Now I want to make a joke about communist music. All right, so we have frequency 1. I want to start with vertex D because it is the most connected. It has the highest degree, so we'll put station D there. Looking at my degree 3s, which are next, looks like we need another channel. So frequency 2. Okay, with frequency 2, we're going to make that blue. Okay, so put B on that. I also have A here. A has degree 3. It can't be blue. It can't be red. Looks like we need another color. Okay. I'm going to make that black. Okay, vertex E can't be blue and it can't be red, but we could make that black. Vertex C can't be red, but I could make it blue. And vertex F can't be black, but I could make this blue or red. So answers vary here, a couple different correct ways to color this. But it would take me 3 frequencies to make this happen. Okay. So on your homework tonight, you're going to have a problem kind of like this. Only it's going to be about fish, that if they're in the same tank, they will eat each other. So you need to make sure that fish that will eat each other are not in the same tank with each other. Therefore, they're not in the same color of tank. Okay. Now, next time, we are going to go on to something called a dual graph, but we're not going to do that today. Okay, for today, you're going to get a handout that you are going to color. All right, and the handout looks a little bit like this. Oops, wrong one. Okay. So it starts off, possibly, if it'll open. Okay. So you're going to have compatible. So it says, color the following as described so that no two adjacent vertices are the same color. And if it's not K color, say impossible. So you're going to use 4 colors and then 3 colors and then 2 colors. And if you have one that isn't possible, you'll just cross it out or say impossible. And then the chromatic number would be the fewest number of colors you actually need. Now you may have to play around with a couple of these. Just because you don't get it on the first time doesn't mean necessarily that it is impossible. Okay, so you have some chromatic numbers just like in the notes that you're going to be playing around with. There's a complete graph, there's a tree, there's some circuits. Here's a tropical fish problem. So this is going to be like our graph O hatred, but instead of A not being able to just like or sit at the same table as C and B, we need to be more careful because if A is sitting in the same tank as B, they will eat each other. All right, so that is a problem. So we want to make sure you have connections to show that they wouldn't be able to be in the same color. Also, just because A can't be with B and A can't be with C doesn't necessarily mean they can't be with each other. You would have to go on to B and C to see if that would be the truth. Here it says the number of tanks needed, so you can color your tanks and fill them in. If there are certain tanks you don't need, you don't have to fill those in. Okay. Now, the last page of your homework is going to have some coloring on here, and it's going to have a couple little towns that you're going to color, a couple little maps, and you're going to use your coloring rules. Just as a reminder, on this last page you can only use 4 colors, and this last page will also be graded on accuracy. So what I mean then is that if on this Boxberg graph, for example, if you color this edge red and then you color this edge red, okay, I'm going to circle this little border right here, and I'm going to say -1/2. Okay, now each of these last are only worth 1 point, so you can still, if you make 2 mistakes, I won't take out more than 1 point for it, but you will lose a point if you have any inaccuracies. So these will be graded on accuracy, these last 4 questions. The rest of the assignment will be graded on completion. So get your coloring supplies ready and have fun.